I'm glad to provide a refresher on quantum mechanics and summarize our previous discussions. Quantum mechanics is a branch of physics that deals with the behavior of particles at the atomic and subatomic levels. Here are some key points we've covered. Quantum mechanics describes the dual particle-like and wave-like behavior and interactions of energy and matter. It introduces the concept of probabilities and uncertainties in the behavior of particles, unlike the deterministic nature of classical mechanics. We've discussed the incompatibility between quantum mechanics and general relativity, highlighting that while quantum mechanics excels at explaining phenomena at small scales, general relativity is effective at large scales like celestial bodies and the universe's structure. The quantum field theory combines quantum mechanics with special relativity and treats forces as local interactions through the exchange of particles. We've also touched on the search for a theory of quantum gravity that can unify quantum mechanics and general relativity in a consistent way, especially significant in areas like near black holes or during the early universe. These topics represent some of the fundamental concepts and challenges in the field of quantum mechanics. If you'd like to delve deeper into any specific area or have more questions, feel free to ask. In physics, recalibration is often necessary when dealing with instruments or experiments because different conditions can affect measurements. For example, as you mentioned, altitude can affect an alcohol breathalyzer's readings due to changes in air density and pressure. When it comes to classical physics versus quantum physics, the need for recalibration is more about using different theories and equations that are appropriate for the scale you're working with. Classical physics, governed by laws such as Newton's laws of motion and Maxwell's equations, works well at the macroscopic scale we experience in everyday life. However, when you delve into the atomic and subatomic scales, quantum physics takes over with its own set of principles and equations like the Schrödinger equation for wave functions. The formula E equals mc squared from Einstein's theory of relativity is a separate consideration. It relates energy E to mass m, with c being the speed of light in a vacuum. This equation is part of the broader theory of relativity, which deals with the physics of high speeds and large gravitational fields, bridging some aspects of classical and quantum physics. So, in essence, while you don't recalibrate the physics per se, you do switch to different models and equations that are designed to accurately describe phenomena at different scales or under different conditions. Each set of physical laws has its own constants or parameters that are used in their respective formulas, and these are determined through experimental evidence and theoretical calculations. In quantum mechanics, light is described as being made up of particles called photons. Photons are quanta of the electromagnetic field, which includes light. Quantum mechanics shows that these photons can exhibit both wave-like and particle-like properties. The speed of light in a vacuum is a fundamental constant in physics, denoted as c, and is the same in both the classical and quantum worlds. It is approximately 299,792,458 meters per second. This speed is considered the ultimate speed limit for the transfer of information in the universe. Even in the quantum realm, where particles can exhibit strange behaviors like quantum tunneling, the speed of light remains a core constant of nature. However, there are phenomena in quantum mechanics, such as quantum entanglement, that seem to involve instantaneous interactions between particles over a distance. These phenomena do not actually transmit information faster than light. They are subtle and complex interactions that are still bound by the principles of relativity, which assert that the speed of light is the same for all observers, regardless of their relative motion or the motion of the light source. So, while quantum mechanics can predict some behaviors that seem to challenge our classical understanding of speed and causality, the speed of light remains consistent across both classical and quantum physics. The properties of light at the quantum level are deeply intertwined with its wave-particle duality, which is a central concept in quantum mechanics. Certainly. Let's clarify the concepts of waves and particles in physics. Wave. In physics, a wave is a disturbance that transfers energy through space and matter. It is characterized by its wavelength, frequency, and amplitude. Waves can be mechanical, like sound waves that require a medium to travel through, or electromagnetic, like light, which does not require a medium and can travel through a vacuum. Particle. A particle is a small localized object that can be described by properties such as volume, density, or mass. In classical physics, particles are considered to be discrete packets of matter or energy. Now, wave-particle duality is a fundamental concept in quantum mechanics that tells us that quantum entities like photons and electrons exhibit both wave-like and particle-like properties, depending on the experimental setup. This duality is a cornerstone of quantum mechanics and helps explain behaviors that cannot be fully described by classical physics alone. For example, light can behave like a wave when it undergoes interference and diffraction, but it also behaves like a particle when it interacts with matter in the photoelectric effect, where it knocks out electrons from a material. Similarly, electrons, traditionally thought of as particles, can exhibit wave-like behavior, such as creating interference patterns in a double-slit experiment. The wave-particle duality is not about an entity switching between being a wave or a particle, but rather that it inherently possesses both sets of properties simultaneously. It's a unique aspect of quantum mechanics that challenges our classical intuitions about the nature of reality.